In rigid body mechanics, today we are going to start a very important problem of this chapter. And this is actually the problem of dealing with motion of a heavy symmetrical top under the action of gravity. In fact, this is the most important concept of this chapter and also very important for your examination. Okay, this is actually in the syllabus of both B.Sc level students and M.Sc level students. So actually this discussion is very rigorous and somewhat lengthy too. Therefore, for convenience, I will divide my lecture on this motion of symmetric heavy top under the action of gravity actually in two parts. Okay, so this is actually the first part of the lecture on this subject. And in this first part of the lecture, we will see the basic equation. Okay, and after that, you will see the solution of that very basic equation to deal with this problem under certain conditions. Because in general, the final equation which we will obtain, the solution of that very equation is very tedious. Okay, that's why we seek the qualitative actually explanation or qualitative solution of that very equation by in a particular condition, in some particular conditions. So now let us start to know about the motion of a heavy symmetrical top under the action of gravity. In fact, when you say symmetric top, what does it mean? Actually, the symmetric top that we are going to discuss here is approximated to a variety of rigid bodies. For example, you can take, you have seen a child's top, gyroscope. These are some of the important examples of symmetric top. Okay, and we have to discuss its motion in the present problem. So now let us see this figure. I have drawn here the theoretical figure for understanding the concept of motion of symmetric top under gravity. Okay, and so you can see we consider a spinning symmetrical top in uniform gravitational field. It means the acceleration due to gravity is constant here. Okay, and this spinning top is fixed at one of its points, let us say at O, which is taken actually as an origin, and the axis of symmetry, okay, is which is fixed in space that passes through this fixed point O. Okay, as I have told you that such a top is called a heavy symmetrical top, and for example you can see the child's top, gyroscope, etc. Okay, now let us consider that this point G, you can see the figure, this is the center of gravity of the top. Okay, and I have assumed that this L is the distance of center of gravity of this body from the fixed point O. Okay, so L is its the distance of center of gravity from point O. You can see in this figure. Okay, actually for discussion, you can take the symmetry axis as one of the principal axes, and let us choose it as this Z prime axis. This is the body axis and also symmetry axis, and this can be taken as one of the principal axes for simplicity, for calculation. Okay, and as you have considered that Z dashed axis is one of the principal axes, so definitely the other two body axes, which will be X dashed and Y dashed, okay, are these are actually the other two principal axes. because you consider z dash as principal axis, so the other two body set of axes, that is OX dash axis and OY dash axis, will be definitely the other two principal axes. Okay, and actually in this condition, since the body is fixed at O and the axis of symmetry is z dash, so the principal moment of inertia of this body about the other two axes, that is x dash axis and y dash axis, will be equal. So you can write that I1 is equal to I2. You know, I1 is the moment of inertia of the body about the first principal axis, that is x dash axis. I2 represents the moment of inertia about the second principal axis, that is y dash axis. Okay. So in this condition, I1 will be equal to I2. So always keep this fact in mind, because this will be needed in your calculation. Okay. Now, the only force acting on this rigid body is the force of gravity. If you assume that m is the mass of the rigid body, then the force of gravity, which will be equal to mg, that will act in vertically downward direction at center of gravity. Okay. So if g is acceleration due to gravity, the force of gravity will be mg, and that mg acts in vertically downward direction at this point g, which is center of gravity. Okay. This is the only force which acts on this symmetric top. Okay. Now, we also consider here the body set of axes. You can see this x-axis, y-axis, and this z-axis. These are the these are the space set of axes, or you can say these are the fixed set of axes. Okay? And you can see that actually the x and y axes are in the horizontal plane, and this z axis is in vertical direction. Okay. So I have marked here the word vertical, you can see. Now, as the body is fixed at point O, okay, so the motion of this symmetric top can be described in terms of the three Euler's angles, you know, phi, theta, and psi. Because you have learnt in my previous video that if a rigid body is fixed at a point, then only rotational motion is possible. And that rotational motion can be completely described by taking the three Euler's angles, which are actually angles of rotations, phi, theta, and psi, as generalized coordinates. So in this case, the most suitable set of generalized coordinates will be phi, theta, and psi, which are actually the Euler's angles. Okay? In fact, our aim in taking up the present discussion is to deal with the interaction of various types of motion that the top executes. Okay? And as you know, that apart from the translational motion, the top has actually three types of motion. Okay? And what are actually those three types of motion? Let us see. What I have explained, I have noted down here for your convenience. You can note down these things in your notebook. I always tell these things to you. And that will be very helpful for your examination purpose. If you can actually pause the video, write down in these things in your notebook, and then whenever you will revise it, that will be very helpful to you. Okay? So all these things which I have explained just have been written here for your convenience. Okay? Now, as I have told you that apart from the translational motion of this top, actually there are three types of motion. The first one is called precession. The first one is called precession, or precessional motion. Actually, what is this precession? In fact, this precession is rotation about the space z-axis. See here, this precession is rotation about this space z-axis, as you can see in this figure. Okay, and such a rotation actually correspond to the Euler angle phi. Okay, that correspond to Euler angle phi. So phi determines, this rotation angle phi determines the precessional motion of this rigid body or this top. The another motion which our top can perform is called nutation. Okay, we will learn about these things in very detail in the second lecture. Okay, and what is this nutation? Actually, nutation is the rotation about line of nodes. You can see this intermediate x1 axis in this figure here. You can see this is your line of nodes. You can say that this is x1 axis. This is between x and x dash. X is a space set of x axis and x dash is body set, and this line of nodes lies between them. Okay, so the another angle of rotation which is marked by this phi, that is actually rotation about this line of node, and angle of rotation is represented by the symbol phi, which is actually the second Euler angle. Okay, and this Euler angle phi actually not phi but theta, not phi but theta. This actually determines the nutational motion, or you can say nutation. I have marked here this. Okay. Now, the third motion the top executes is called a spinning motion. Okay, I have considered, actually in the very beginning I have told you that we consider a spinning symmetrical top. Okay, and this spin is what? Don't confuse this spin with the quantum mechanical spin. Classical spin is associated with motion, but quantum mechanical spin is an intrinsic property of particle that is not associated with any motion. So here a spin is a type of motion, and this is actually in this present case rotation about z-dashed axis. Z-dashed axis is actually here the axis of symmetry or the body z-axis, and this spin is actually the rotation about this body set of z-axis, or you can say the axis of symmetry, and this rotation corresponds to angle psi. Okay, so these three type of motion apart from the translational motion of a rigid body are possible. Okay, now our aim is to discuss all these types of motion here, and we will actually follow or adopt the Lagrangian formulation of mechanics to discuss the problem of motion of heavy symmetrical top under gravity. And so first of all we will try to find the Lagrangian for this system. You know, Lagrangian of this system L in general is defined by T minus V. This is general definition of Lagrangian, where T, you know, is kinetic energy of the system and V is potential energy. Now, as our rigid body here is rotating about the three principal axes, so you should think the expression for rotational kinetic energy in terms of principal moment of inertia. And I have provided an independent video on the discussion of rotational kinetic energy of a rigid body, where I have talked about this. And you know, with respect to the principal axis, the rotational kinetic energy is given as half I1 omega 1 square plus 1 over 2 I2 omega 2 square plus 1 over 2 I3 omega 3 square. But remember, I have told you in the beginning that in present case I1 is equal to I2. I1 is equal to I2. So I have taken here I1 as a common factor in the expression for t. So L is given as 1 over 2 I1 times omega 1 square plus omega 2 square and plus 1 over 2 I3 omega 3 square. This is actually the expression for kinetic energy of this body. Here you know omega 1, omega 2 and omega 3 are the components of angular velocity of this body along the three principal axes. Okay, these are components. These are also denoted by the symbol omega x dashed, omega y dashed and omega z dashed. Okay. And what will be the potential energy of the body? You know, since this rigid body is not a point mass, okay, its mass is distributed in a volume. So you can find the potential energy by a simple technique. You know, if mass is distributed, then we can follow a very simple technique to obtain the expression for potential energy of such a body. You know, center of gravity of a body is defined as a point where the total weight of the body acts. Okay, so you can thought that the total weight, that is mg, is actually acting at this point g. So you can equivalently consider that this body is just equivalent to a point mass whose mass is equal to mass of the body and it is located at the center of gravity. So while finding the potential energy of this body, you can change the nature of the problem. You can think that there is a point mass whose mass is equal to m, which is mass of the rigid body, and it is located at point G. Again, you know, potential energy is a state function. Whenever you have to find the value of potential energy, you must think about a reference level or reference point where you arbitrarily assume that potential energy is 0. Here, we consider this fixed point O as the reference point. It means we will take potential energy V equal to 0 at point O. Okay? Then let us see what is the height of this center of gravity, where we assume that the total mass of the body is lying from this point O, from the reference point. You can see as OG is equal to L. And let us take that this point is P. Then OP is its height. This is H. Now you can see if your aim is to find H and you know L and theta, you can use the trigonometric ratio cos theta. This cos theta will be equal to H over L. Okay? And so H is equal to what? This is L cos theta. Okay? So the problem is now like this. This is a reference point, and at a height H, which is equal to L cos theta, there is a point mass M. So what is its gravitational potential energy? That is simply mgh, but h is L cos theta. So gravitational potential energy of this body will be equal to what? That is mgl cos theta. Have you understand? This is a very simple concept. You have definitely studied these things in your lower classes. Okay. So you can see I have written here that the potential energy of this rigid body is equal to mgl cos theta. Okay. Minus sign is due to here because L is T minus V. So the first two terms represent the kinetic energy of this body, and the last term mgl cos theta, its gravitational potential energy. Okay. And here I have already told you earlier that this I3 is the principal moment of inertia about the symmetry axis. Okay. Now I have provided a video earlier for finding the components of angular velocity of a rigid body along the three principal axes or body set of axes. And in that video, I have told you that those results will be used in the forthcoming video. Now you can see here there is a need to write the expression for omega 1, omega 2 and omega 3 which you have learnt earlier. So I have written the expression for omega 1, omega 2 and omega 3 directly because I have already taught these things to you. So you must remember the expression for omega 1, omega 2 and omega 3 for writing the answer of this symmetric term. You have to remember, okay? You can't derive it. That is another concept. You can remember that we have obtained omega 1 is given as phi dot sine theta sine psi plus theta dot cos psi. Are you getting the things? Definitely you should get. Omega 2, this is phi dot sine theta cos psi minus theta dot sine psi. And omega 3, this is phi dot cos theta plus psi dot. These are the expressions for omega 1, omega 2 and omega 3. Now, we will simply substitute the values of omega 1, omega 2 and omega 3 in the expression for Lagrangian here, which I have defined. At the place of omega 1, omega 2, omega 3, write these expressions, okay, and simplify. So, let us substitute. When you will put at the place of omega 1 this much, at the place of omega 2 this much, okay, and at the place of omega 3 this much, what will be your result? Actually this will be a simple algebra. I have not done those every step of algebra. You can do it yourself, and that is a very simple calculation. So I have directly written, after simplification you will see that L is equal to 1 over 2 I1 times theta dot square plus phi dot square sine square theta plus 1 over 2 I3 and omega 3 square, but omega 3 is this much, so this is psi dot phi dot cos theta whole square and minus mgl cos theta, okay. Now actually after getting the expression for Lagrangian of this system, first of all in the basic theory we are going to find the first integrals of motion. When you say first integrals of motion, it means we have to first of all find the constants of motion. And after getting the expression for constant of motion, we will be able to find the generalized coordinate to deal with the configuration of this rigid body. Okay? Now, for finding the first integral, you will see later on that there are actually three first integrals of motion, equation of motion. And what are those three first integrals of motion? Let us now try to understand. And for this, let us see this equation 1 seriously. See the terms in RHS. If I will ask you, does this Lagrangian L depend on the coordinate psi and phi? Answer is no. Psi and phi directly or explicitly, answer is no. L is an explicit function of theta. Theta is present here. But phi and psi are not present here. So we simply say that Lagrangian is not an explicit function of the coordinates phi and psi. Okay? Or you can say that Lagrangian does not depend directly on phi and psi. And in my previous videos, I have provided an independent video on cyclic coordinates while dealing the problem of Hamiltonian formulation. So if you have not watched my video on cyclic coordinates, you must watch. You may go through the playlist of classical mechanics and search the video on cyclic coordinates. There you will find the complete idea, complete concept of cyclic coordinates. Actually, if the expression of Lagrangian does not involve directly phi and psi, then we say that Lagrangian is not an explicit function of phi and psi. And if Lagrangian is not an explicit function of phi and psi, then phi and psi are called cyclic coordinates or ignorable coordinates. So I have written here, you can see, it is obvious from this equation 1 that Lagrangian L is not an explicit function of the coordinates phi and psi, and hence phi and psi are the cyclic coordinates. Okay? And you know, if phi and psi are cyclic coordinates, then actually the momenta corresponding to the cyclic coordinates are constant of motion. Okay? So the momentum corresponding to the coordinate phi, which will be denoted by p phi, that will be a constant of motion. Similarly, since psi is also a cyclic coordinate, so the momentum corresponding to psi, which is denoted by the symbol p psi, that will be also a constant of motion. And these two constants of motion, p psi and p phi, are called actually the first two integral of motion. Okay? Now we will find these first two integral of motion, that is p psi and p phi. You know, the momentum corresponding to the any coordinate q. If q is a coordinate, then pq is defined as del L by del q dot. This is actually basic definition of momentum. So the momentum corresponding to the coordinate psi, which is a cyclic coordinate, that is given as p psi equal to partial derivative of Lagrangian L with respect to psi dot, where psi dot represents the generalized velocity. So del L by del psi dot, that is actually equal to p psi. Okay? Now, expression for L you can see in this equation 1. And for getting the expression for p psi, what you will have to do? You have only differentiate this equation 1 partially with respect to psi dot. Okay? Then you will get p psi. Let us see. In the RHS of equation 1, you can see the first term does not contain psi dot. Okay? So the derivative of this first term will be 0. That will be omitted. Okay? But the second term contains psi dot. So this will be differentiated. First of all, this will be differentiated with respect to psi dot plus phi dot cos theta. And that will be 2 times psi dot plus phi dot cos theta, and 2 here will cancel. Okay, I3 is a constant, so this will be I3 times psi dot plus phi dot cos theta. Now, this psi dot plus phi dot cos theta will be differentiated with respect to psi dot. So, derivative of psi dot with respect to psi dot will be 1, and that of phi dot cos theta will be 0. So, this is simply psi dot plus phi dot cos theta. Okay. But see, this is psi dot plus phi dot cos theta. This is what? This is actually the third component of the angular velocity vector of the rigid body, that is omega 3. So instead of this psi dot plus phi dot cos theta, you can write omega 3. Okay. Actually, our aim is to express this principal moment of inertia I3, which is about the axis of symmetry, in terms of the principal moment of inertia about x or y axis, that is x dashed or y dashed axis. So we consider for simplicity that this I3 omega 3 is equal to I1 times A, okay, where A is a constant. Okay. Now, in the similar manner, you can find the generalized momentum corresponding to the cyclic coordinate phi, and for this you will have to partially differentiate L with respect to phi dot. Again, see the expression for L in this equation 1. Here, phi dot is content in both terms, first and second both. So let us differentiate it. When you will differentiate the first term, you can see the this will be derivative of theta dot square will be 0, okay, but that of phi dot square will be 2 phi dot, that 2 and here in denominator 2 will cancel out. So the first term is I1 sine square theta phi dot, okay. Now let us differentiate this second term. This is again a function of function, so that will be 2 times psi dot plus phi dot cos theta, and after that you will differentiate with respect to phi dot. So this will be I3 times psi dot plus phi dot cos theta times cos. You can do it. This is very simple differentiation. Okay. Now, as a phi dot is present in this first term and this third term, so let us take phi dot as a common factor, and this is I1 sine square theta plus I3 cos square theta, and the remaining term is I3 psi dot cos theta. And we assume that this is equal to I1b. Here b is another constant. Okay. In this way, we have defined p psi and p phi, which are actually the generalized momentum corresponding to the cyclic coordinates psi and phi. Okay. Now let us see. After getting this two constant of motion or two first integrals, we can think about the next first integral, which is third first integral. And what is that? As you know, here our symmetric top is moving under gravity, and you know, force of gravity is a conservative force. So you can say that the motion here is taking place under conservative force, and so this system is a conservative system. And you know, in case of a conservative system, the total energy is constant. It does not depend on time or position. So the total energy of this system will be also the constant of motion, or you can say the first integral of motion. Okay. So the next first integral of motion is total energy of the system, which is denoted by the symbol E, and you know E is equal to sum of kinetic and potential energy, that is T plus B. Now expression for T and V, you know, this is in the expression for Lagrangian, this first two term, the sum of first two term, this actually represents the kinetic energy, okay, and the last term potential. So here at the place of T, you can write this much. This is half I1 times theta dot square plus phi dot square sine square theta, and plus 1 over 2 I3 omega 3 square, because this psi dot plus phi dot cos theta, this is equal to omega 3, okay, and this is potential energy mgl cos theta, okay. So this is the next first integral of motion, which is actually the total energy of this system, which will remain constant, okay. Now our aim is actually to find the generalized coordinates, and for this we will have to solve these equations. So let us first of all see this equation number 2. See here. Here you can see that this I3 psi dot plus I3 phi dot cos theta, that is equal to I1 A1, okay. So from that equation, I3 psi dot can be written as I1A minus I3 times phi dot cos theta, okay. Now we will use this equation 5 in equation 3 at the place of this I3 psi dot. You can use this result. So I3 psi dot, which we have obtained, that will be substituted here in this equation 3, and after that you can see this is I3, sorry, I have written this first term here, okay, at each. And at the place of this I3 psi dot, we will use that result. So you can see the first term is at each here, okay, and this is at the place of I3 psi dot, okay, at times cos theta, so this is, and that is equal to I1b. You can see equation 3. Now, simplifying this equation, we will find the expression for phi dot. Algebra is very simple. You can see the first term is I1 phi dot times sin square theta plus, here the first term is I1a cos theta, okay. Now, inside the first bracket, the second term is I3 phi dot cos square theta, and here in the second term is minus I3 phi dot cos square theta. You can see these two terms will cancel out, okay, and that's equal to I1b. Now, I1 phi dot sin square theta, you can see this is I1 times b minus a cos theta. I have brought this term in LHS, now in RHS, okay. Now you can see that this I1 and this I1 will cancel out, and so phi dot is equal to this much. This is b minus a cos theta over sin square theta, okay. Now this value of phi dot, which we have obtained in this equation 6, now let us use this in this equation 5. See here, at the place of this phi dot, use this value, okay. So after using equation 6 in 5, what will be our result? You can see this will be I3 psi dot equal to I1a minus I3 times b minus a cos theta over sin square theta times cos theta, okay. Now psi dot will be what? We will divide the RHS by I3. So this is I1 over I3 times a minus, in second term I3 will cancel out, and the second term is b minus a cos theta over sin square theta times cos theta, okay. So this is the value of psi dot, okay. Now the values of phi dot and psi dot, which we have obtained in this equation 7 and 6, actually these two values will be now used in equation 4, okay. That is the equation for energy. See equation 4 here. This is equation 4, which defines the energy of this system. And in this expression, at the place of phi dot and at the place of psi is not directly present here, but we will actually use this result here. So see, after substituting this value, E will be equal to half I1 theta dot square plus half I1 sin square theta times, here there is actually phi dot square, and phi dot is this much, okay. So this much square, and plus 1 over 2 I3 omega 3 square. But you have seen earlier that I3 omega 3, you can see here, I3 omega 3, this is equal to I1a. I3 omega 3 is equal to I1a. I3 omega 3, this is equal to I1a. So omega 3 will be what? This will be I1a divided by I3. So at the place of omega 3, I have written this much, okay, and plus mgl cos theta. Now one of this I3 will cancel in this term, you can see, because in denominator there is I3 square. Now bring this term in LHS. So your equation becomes E minus I1a square over 2I3, and that will be equal to 1 over 2 1 over 2 I1. Here there will be I1. I1 theta dot square plus 1 over 2 I1, and here this sine square theta here in numerator will cancel, because in denominator there is sine 4 theta. So in denominator there remains sine square theta. Okay, and plus this much. Now each term in this expression will represent energy. So E minus I1A whole square over 2I3, this will also represent some value of energy. Let us use the symbol E dashed for it. So instead of E minus I1A whole square over 2I3, now let us write E dashed. Okay, and then our equation becomes E dashed equal to 1 over 2 I1 theta dot square plus 1 over 2 I1 times B minus A cos theta whole square over sin square theta, and plus MGL cos theta. Okay. Now you can see that this first term 1 over 2 I1 theta dot square, this is expression for kinetic energy. Okay. So the remaining term, the sum of the remaining two terms will definitely represent the effective potential energy, or effective potential you can say. Okay. And if you denote this effective potential by the symbol V, which will be a function of theta, you can see, then this V of theta is given by 1 over 2 I1 times B minus A cos theta whole square over sin square theta plus MGL cos theta. Okay. And therefore, if you write V of theta instead of the sum of the last two terms in equation 8, then E dashed can be written as 1 over 2 I1 theta dot square plus V of theta. Okay. And therefore, 1 over 2 I1 theta dot square, this is E dashed minus V of theta, and therefore theta dot, which is d theta by dt, that will be equal to this much. This is a square root of 2 over I1 times E dashed minus V of theta. Okay. Now from here we can find t as a function of time. So after integration, you can see integral of dt from 0 to t, that will be equal to integral from theta at 0 time. Here theta in the argument I have written 0, which represents the value of theta at t equal to 0. And theta of t, it means value of theta at time t. Okay. And d theta over a square root of 2 over I1 times E dashed minus V theta. Okay. Actually, you can see in this way, this t will be obtained as a function of theta. Okay. Actually, this equation in principle can be solved to obtain theta as a function of time. That is theta equal to theta t. Okay. We may substitute theta equal to theta t in these equations 6 and 7, and after integration you will get phi and psi, because this equation 6 defines phi dot, which means d phi by dt, and this equation 7 defines actually psi dot, which means d psi by dt. So after integration, phi as a function of time and psi as a function of time may be obtained. Okay. Thus we have obtained the three Euler's angle, you can say phi, theta and psi, which specify the orientation of rigid body at any moment, any time. In fact, we find that the problem looks to be completely solved, but the solution of theta as a function of time involves the use of elliptic integrals, and the solution of elliptic integrals is very complex, very complicated. So to get the qualitative result in simple manner, we discuss alternative way which will deal the phenomenon in a qualitative manner. But how those problems will be dealt, we will learn in our forthcoming video. As I've told you earlier that we will divide this lecture in two parts, and this was the first part in which we have obtained this basic result or basic principle we have seen. But in the next lecture we will discuss the different type of motion of the symmetric top, like precessional motion, nutational motion, precession without nutation, precession with nutation. These things we will discuss in our forthcoming video. I think you have clearly understand the ideas which I have discussed here. Okay, thank you very much.